In this lecture, I will show you what is the most general form of the additive law of probability. Then I will point out a pattern that you can easily memorize the result. After that, we'll use a Venn diagram to illustrate the idea before finally proving the case of 2 and 3 events. Right, let's get started. The additive law of probability, when you have 2 events, A and B, it says probability of A union B is probability of A plus probability of B minus probability of A intersection B. The case of A, B, C, 3 events, the law is following. Which has a very nice and easy to remember pattern. First of all, you add the probabilities of one event, A, B, C, and then you subtract the probabilities of intersections of 2 events, which would be AB and then BC and then AC. Finally, you add the probabilities of any 3 events. In this case, there is only one of them, which is A intersection B intersection C. You see, here you have switching sign from plus to minus to plus. So we can easily generalize this to even more events. For example, if you have A, B, C, D, the probability of A union B union C union D is then the first one is plus probability of A plus probability of B plus probability of C plus probability of D. Right? Then minus the probability of the intersection of any 2 events. In this case, would be AB, AC, AD, and then BC, BD, and finally CD. And the next row would be your changing sign from minus to plus, the probabilities of any 3 events, which is A, B, C, and then A, B, D, and then A, C, D, and finally B, C, D. And the last group here, you're switching sign again to minus, which is the probability of any 4 events. In this case, there's only one of them, A, B, C, D. Now, let us explain the idea through the Venn diagram. If you have 2 sets A and B, so here is A intersection B is which is this blue part. And we can see that this part is counted twice by, if you simply do probability of A plus probability of V, you're counting this part twice. So you need to subtract one copy, and that's the formula for this case. In the case of 3 sets, idea, by adding PA, PP, PC, you are counting A intersection B twice, B intersection C twice, and A intersection C twice. So you need to subtract all of them. But then by subtracting all of them, you are actually, this is the part, the black part is A intersection B intersection C. You're actually adding it 3 times and subtracting it 3 times. So you need to add 1 copy back. That's the final part of probability, adding probability of A intersection B intersection C. Alright, so how do we actually prove it? Prove them using only the basic axiom. In the case of only 2 events, the proof is actually very simple. So the probability of A union B, here is A, here is B, the idea is that we split A union B to be 2 parts. A union B to be the blue part, which is A, and then the magenta part, which is B minus A intersection B. Notice that that is a mutually exclusive union. So by the third axiom of probability, we know the probability of A union B is probability of A plus probability of B minus A intersection B. All right. On the other hand, by looking at the probability of B, we know that the probability of B is equal to the probability of A intersection B plus the probability of A B minus A intersection B. The reason is the same because B can be written as A intersection B union B minus A intersection B. So this is again a mutually exclusive union. We can use the third axiom of probability again to prove them. By combining these 2 identities, we know that the probability of A union B is then the probability of A plus this guy. But from the second identity, we know this is the same guy here. That guy is equal to, from the second identity, we know that's probability of B minus probability of A intersection B. So that's the end of the proof. Now, the case with three sets, A union B union C, we can use the common trick of how we go from 2 to 3, or in general, how we go from k to k plus 1. So we view this as two sets, a union of two sets. One set is A union B, and then another set is C. Then we can use the identity we have already proven, which is probability of A union B plus probability of C minus probability of A union B intersection C. We use it again to rewrite this as probability of A plus probability B minus probability of A intersection B. So that's that part. And we rewrite the remaining terms. And for the last one, we use the distributive law, which means A union B intersection C is A intersection C union B intersection C. And then we use the identity for a third time on the final term. Probability PA plus probability of B minus probability of A intersection B plus probability of C minus that term would then be probability of A intersection C. So you think of them as two sets, plus probability of B intersection C minus probability of A intersection C intersection B intersection C. So use that identity for a third time. Then it's a matter of grouping them. This can be beautifully rewritten as probability of A plus probability of B plus probability of C minus probability of A intersection B, probability of A intersection C, probability of B intersection C. And the only term remaining is, notice that here we have minus and another minus, so that becomes plus, and A intersection C intersection A intersection C intersection B intersection C, that is simply A intersection B intersection C. So that is the end of proof for the case of 3. We can actually prove this general form by inducting on K, the number of sets in the most general case. That's it for this lecture.